another RLC circuit here, except this one's going to be a little bit different. So we're going to have power supply right here. Let's say the power supply is 2.2 kilohertz at 15 volts RMS. And so it's connected up to a resistor right here. Resistor is 330 ohms. And then it's connected to a capacitor and an inductor like this. Okay, so let's say the capacitor is 0.12 microfarads and the inductor is 18 millihenries. And so I want to know several things here. I want to know what is the current in here and what would be the power that is supplied. Okay, so to find the current's pretty easy. Current is going to be equal to V over Z. So I got to find Z. Well, the problem is that in the book and in the lecture, we've talked about series RLC circuit. This is not in series. This is not going to be parallel either, because they're not all in parallel. We did an example like that. Now, at very high frequencies, you can say, oh, wait, at very, very high frequencies, then it's going, then all the current is just going to go shunting through the capacitor. That's going to act like just a wire, so it's going to be 330 ohms. So Z at high frequency is going to be 330 ohms. But Z at low frequency is also 330 ohms, because now then the inductor is going to act like a wire. But we're not at high or low frequencies. We're at 2.2 kilohertz. That's going to be in between the extremes. So we're not going to be either of those extremes. So we need to figure out what is this impedance going to be. Well, the nice thing here is this kind of adds up pretty much as you might expect. Okay, so we have current here, and that's in series with this parallel part over here. Okay, so that means that this is going to be in series with the parallel part. Well, the parallel part, okay, so what's this parallel part going to be? Well, the impedance of the parallel part is going to be, those two are in parallel, right? So the impedance of the parallel part, so this is the parallel part, is just going to be, it's going to be equal to 1 over XL minus 1 over XC to the minus 1, actually absolute value of that. So it'll be the absolute value of that. Okay. Now, so you would think naively that the total impedance would just be R plus 1 over XL minus 1 over XC to the minus 1. And that would be wrong. Why is that wrong? Well, because we know that the current is in phase with the voltage here, but for both of those, the current is 90 degrees out of phase with the voltage. So that means that 90 degrees out of phase, again, think about how we added the phasors. So if we think to how we add the phasors, they're 90 degrees out of phase. So if they're 90 degrees out of phase, then the Pythagorean theorem holds. So that means this is really going to be square root of R squared plus 1 over XL minus 1 over XC to the minus 2. Okay, so the minus 1 and then squared. Okay, so that is actually going to be the impedance for this circuit. Okay, so if you plug in our numbers that we've got, so the impedance is going to be equal to the square root of R, 330 ohms squared, plus 1 over 2 pi 2.2 kilohertz. We got to like convert that into hertz. So 2,200 hertz times the 0.018 henries minus, that turns out to be 2 pi, so it's going to be 1 over that. So 2 pi, 1 over 2 pi is 2 pi. So 2 pi 2,200 hertz, and that's going to be 1.2 times 10 to the minus 7 farads. Okay, all of that to the minus 2. Okay, do all that, the impedance comes out to be 537 ohms. So the current will be V over Z, so that'll be 15 volts RMS divided by 537 ohms. So the current turns out to be 27.9 milliamps RMS, or in other words, that's going to be 0.0279 amps RMS. All right, so that is the current in there. Now notice what we had here. For this circuit, in which we had the resistor, and then we had the capacitor and the inductor. Now notice that's not exactly how I drew it last time, but this does exactly the same thing, okay? In this case, it actually, unlike the series RLC circuit case, in which you had a resonant, and at resonance you had the minimum value. Here at resonance you have maximum value, okay? Because, you know, look what's going to happen here, okay? So Z equals square root R squared plus 1 over XL minus 1 over XC to the minus 2. Well, what's that going to do? When XL equals XC, then that is going to go towards infinity. So that means that at resonance, this is not going to pass any current. And so since it passes no current at resonance, and it passes current above resonance and below resonance, there's no current pass at all at resonance. The minimum current is going to be there. Maximum current is going to be at really high frequencies or really low frequencies. But at resonance, no current flows. So we sometimes refer to this as an anti-resonant circuit. Okay. So what's the power? So we want to find the power. Power is going to be IV cosine phi. So how do I find phi? Well, it turns out all we need is cosine phi. Now remember, on the phasor diagram, we've got the VR this way, we've got the total V some other direction right here. The current is going to be perpendicular, and the current is going to be perpendicular here through the in other words, the voltage is going to be perpendicular on the LC part. Okay, so the total voltage is going to be like that. So we just need that component right there. Well, we know that that is going to be in the direction of the impedance of the LC part. That's going to be in the direction of the impedance of the resistor. That's the resistor, so that's going to be the direction of the impedance. So all we really want is the cosine phi is going to be given by R over Z. Okay, so we don't even need to figure out phi. We just know that the cosine phi is R over Z, and we actually have those values right. So the power is going to be equal to IV R over Z. And so that's going to be equal to 0.0279 amps, okay, RMS, times the voltage, which is going to be 15 volts RMS, and that will be 330 ohms divided by 537 ohms right there. And so the total power turns out to be 0.257 watts.